Hello, my name is Rafal Chojna. I work at Wolfram Research as a consultant. I work remotely from Poland. My talk will be about LibraryLink. I will present a few tips and tricks on how you can make your code faster, more memory efficient, and more elegant. So let me start with a picture here. So you can see the programming world that we currently live in. So I assume we all here use the Wolfram language, so I placed it in the center. But around us there are also other popular languages like C, C++, or Java. And all right. Is it better now? Is it better now? Okay. Great. So it so happens that we can use all those libraries written in other languages from within the Wolfram language. And to achieve this, we use something called links. So for example, for Java, we have JLink. And for C and C++, we have LibraryLink. And this is the topic of this presentation. But I will not provide a detailed overview of the LibraryLink, and instead I will just give you a few loosely connected tips and tricks about this framework. So the first thing I would like to talk about today is our so-called passing modes. So if you recall the usual invocation of library function load, as the first argument here is the library name, then we have a function name, and there comes the argument specification. So this is a list of types of input arguments. And as you know, if we want one of the arguments to be a tensor, we shall provide a list like this. When the first element is the data type, here in this case it's integer, but for tensors we can also use real or complex. And the second element of the list is the tensor rank. So this can be any natural number. You can also use an underscore, so this is like a match all pattern. And basically that's it, but there is also a third element which can be omitted, and in which case it's automatic. And this is the passing mode. So it determines how the tensor is passed to the library code. So the default one, the automatic, means that what you get in the C code is a copy of the original tensor. And that copy is automatically cleaned later. So this is like the safest possible option, because you can't accidentally overwrite the original data, and also you don't have to manually manage the memory after a function returned. But as you probably know, this is not the most efficient one, because you need to make a copy of the tensor. So in many cases, when you only intend to use the tensor in a read-only manner, you can specify a constant passing mode like this. And here, what you get in your library function is a reference to the original tensor. And yes, and this reference should not be modified. But we also have two other modes. For example, if you want to modify the data, so you want a copy of the original tensor, but you don't want it to be automatically cleaned after the function returns, you can use the manual mode, and then you become responsible for the memory management. And the fourth option is the shared one. So if you intend to have a tensor that is passed from the top level code to the library, then back, then some modifications, may be done, and then the tensor is again passed to the library, then it makes sense to use the shared mode. So you have this tensor that is owned by both the top-level code and the library, and you're only passing the reference to it. So in that case, LibraryLink it maintains a certain table of shared objects, and it counts the references. And if you are not convinced if these types are that important, if these passing modes are that important, then let me demonstrate it. So what I do here is that I have a demo library with a demo1 function. So this function is not very sophisticated, and basically creates a new tensor here, and it copies some data to the new tensor, and it returns it. So here I am loading this demo1 function with 3 different passing modes. Yes, with automatic, constant, and shared. And let's see how this performs. Oops. All right. So I'm calling this function with a tensor of different size. And as you can see, the constant and shared modes are, well, perform similarly, and about twice as fast as the automatic mode. And this makes sense because we create one tensor inside the function, but in case of automatic, there is another copy made, yes, because we need to copy the input tensor. So the bottom line here is that if you don't intend to modify the tensor contents, just use a constant mode or something that does not make a copy. And one thing that I should mention here is that
so what's the difference then between a constant and shared internally? What actually, if it's shared in the same space?
Yes.
What's
So
the
the difference is that in case of a shared vector tensor, the LibraryLink maintains a certain table of shared objects, so it counts the references. I mean, it's aware that you are this tensor is shared between the library and the top-level code. And in case of a constant tensor, you only get the reference, but this is not internally managed by the LibraryLink. All right, so yes, one short warning here. Basically, do not do what I did in the previous slide. So it turns out that if you want to have one function and load it with different passing modes, it may not end well, because if you want to write your C code here, your C function, and you receive the tensor, there is basically no way to determine what passing mode was used in this case. So you can't write a generic code that will do the cleanup if the passing mode was, for example, manual, and skip it otherwise. So the thing is that you should decide beforehand what passing mode would be used with this function, and just stick with it. Okay, so together with passing modes, we also have return modes, but in this case we only have two different modes. Yes, so the default is the automatic. So basically, when your function returns, the LibraryLink takes ownership of the tensor, so you don't have to worry about freeing the memory. And if you want to have this tensor shared between your library and between the top-level code, and then you can use it with shared mode, and the ownership is shared between the library and the top-level code. So you can prolong the life of this tensor in your library. And so far, I've only been talking about mTensor, but those passing and return modes, they also apply to other LibraryLink data structures like sparse arrays and images, and also row arrays. So now you're probably wondering what a row array is, and that's okay because this is not documented. Well, if you're a keen observer, you may have noticed that in Wolfram library.h, in an argument definition, we have this, one of the possible types is mRawArray. But you know, if you want to learn something more about it and go to our reference page for LibraryLink, you will find nothing. But as it turns out, a lot of people actually started using it. So here is a query on Mathematica Stack Exchange with about 30 results. So now let me tell you a few words about a row array. So first of all, the most important thing is the disclaimer that the row array has not been documented yet and officially released. So basically, whatever I tell you today, tomorrow may no longer be true. But anyway, here is an example how to create a row array in top-level code. So you pass a list of elements. So these are the contents of the row array, and there is the underlying type. And in return, you get this nice box with an icon and a short summary here. And to get the data back, you have to normalize the row array. So what's so nice about row arrays is that they occupy less memory than tensor with the same contents. So for row array, we have 101 bytes in this case, and after unpacking, it's 160 bytes. And as you can see in the plot here, I'm creating row arrays and tensors of increasing size, and I'm adding small integers to these containers, so 8-bit integers. And as expected, the row array size, it only grows about 1 byte for a new element. And in case of tensor, the size grows much faster. And the underlying reason for that is that in row arrays we support multiple types. So if you recall, for tensors we only had 3 different types: integer, complex, and real. And now there are many more. So if you intend to only store small integers in your container, then you can use a row array with integer 8 type, and it will occupy less space than the tensor. So when you create your row array in Wolfram language, you should use these names for types, and you can also create the structure in your library code, and in this case, these are the identifiers. So as for the functionality of row arrays, it's very similar to mTensor functionality. Yeah, so interface is basically the same, but of course with different function names. And okay, so the bottom line here is that we have a new memory efficient container, which is not documented yet, so you can use it at your own risk. But it's very efficient compared to mTensor. And the next thing I would like to talk about is about a different kind of performance, mainly about the code quality and maintainability. So here what we have is a Wolfram language with LibraryLink. They are kind of grown together. And suppose we want to link a C library. So in that case, everything is fine because LibraryLink has a C interface, and library is also in C. So the code you need to write will fit nicely here. So, and that is okay. But it often happens that the library we want to link is written in something more modern, in C++ or C++ 11, 14. And in that case, we need to, before we can link this library with LibraryLink, we need to get rid of all those nice features that C++ provides, like exceptions, templates, classes, etc. So it's not a very pleasant task, but what we are working on right now is to provide a certain additional layer around LibraryLink called LibraryLink Utilities, which aims to provide a modern interface to LibraryLink functionality. And the process of linking this library will be much more feasible. So let me now present you main points of those utilities. So how does it differ compared to LibraryLink? So for example, the main thing is that in LibraryLink, as this is written in C, there are no namespaces and no classes. Well, of course, they are somehow simulated by adding prefixes to function names, but that's not what we really want. So in those utilities, we just wrap the existing structures into proper classes, and we also make use of the operators that are available in C++. And another thing is that the resource management is also automated. So in C, in LibraryLink, basically the developer is responsible for allocating the memory and deallocating, but in the utilities we have classes, so this is done in constructors and in destructors. So you don't need to be afraid that you will forget to deallocate the memory. So as soon as your container goes out of scope, the memory will be deallocated. And the next thing, also quite important, is error handling. So as you know, there are no exceptions in C, and we need to utilize those error codes. So each function may return an error, and it's returned as a result. So after each call, we need to check the error variable and properly handle the error if it occurs. And yes, and that's basically for every function. Whereas in C++ and in LibraryLink utilities, you just write the code that you want to write, and the only thing you need to be prepared for is to catch an exception and handle it. And another thing is something called iterators. So there is no thing like that in C and in LibraryLink. So here is a shortcode to sum all the elements of a tensor, whereas in the utilities, where all the containers are wrapped into proper classes, we may equip those classes with methods like begin and end. And in that case, we make use of some built-in features in C++. In this case, these are range-based for loops, and we can also use directly standard functions like accumulate. So we can get the same result in just one line.
Just a question, that range-based iterator in C++ there, that's auto. It's a normal, you could replace that by an mn, couldn't you? Or is it some weirdo type?
This auto here, well, it depends on what's the data type in tensor T.
Sure, but from the example above, it's an mn, right? And so it could be, or is there? It's just a question: is that a weird range-based iterator type?
No. That's just the element type. Of course, it's better to use references here. Yes, I mean, well, in case of amins, it doesn't make much difference, but. If you don't want to copy the element from the container, you can use a reference type. But yes, in this case, this is an int. All right, so I think there's one more feature of LibraryLink utilities, and maybe even the most important one. So it turns out that in case of LibraryLink, one of the problems is that the type of data is not known at compile time. So the data type is stored as one of the fields in M-tensor structure. So to verify if the input tensors, in this case T and S, have the same time, you have to do this if here, and it is evaluated each time when this function is called. So if there is a type mismatch, you need to handle it at runtime. And what's more, as the LibraryLink interface uses different function names for different data types, you need to write the same code 3 times if you want to handle all possible tensor types. So that's not very convenient. And in case of LibraryLink utilities, where tensor is a proper class and it's also templated, so the template parameter is the data type, which means that the type of the tensor is known at compile time. So you may get some help from the compiler to detect all type mismatches. For example, if I were to pass 2 tensors of different data type here, the code won't even compile. Well, and yes, we can also use the swap function here. Okay, so one more thing about the utility. So this is still work in progress. It's not released yet, but actually we are planning to release this library on our GitHub profile. Yes, so Wolfram Research has a GitHub account, and it's possible that quite soon those utilities will be available on GitHub. So you will be able to, fork it, add your own modifications, do whatever you want. But I don't want to make any promises when this will happen. And as for the other useful sources of information, you can always, I recommend reading the official LibraryLink tutorial. And we also have something more general, C++ interface guide. And of course, there is also an active community of people using LibraryLink, so we can check Stack Exchange or our own Wolfram community page. Okay, so that's all I have for today. I think we still have like 2 more minutes for questions, and also the next like 30 minutes I will be downstairs at the image processing booth, so you can catch me there. Okay, so are there any questions right now? Yes?
So when you have an M-tensor that's multi-dimensional, like not just single array,
All right.
the iterators, do they go in row major order?
No, unfortunately, the iterators right now are not very intelligent. So, because the memory is stored in one contiguous part of memory, so yes, it will just go linearly. Yes, of course. All right, so if there are no more questions, then thank you for your attention.